It's my pleasure to introduce our speaker, Dr. Sanaz Zarabi. She's a process development engineer at Beneq, and she holds a PhD in engineering physics from Aalto University, Finland, and specializes in atomic layer deposition and thin film technologies for advanced applications, including optics and quantum materials. So today, Dr. Zarabi will speak on process optimization of thermal ALD thin films for superconducting and quantum computing applications. Case of TFS 200. This talk explores how thermal ALD is optimized to produce high-quality thin films for superconducting and quantum computing using the TFS 200 reactor. So, Dr. Zarabi, over to you.
Hi, everybody. Thank you so much for the kind introduction. So please let me share my screen, and then we can continue. So I think that you can see my screen right now. Am I right?
Yes, we can see your screen.
Okay, so let's start. So thank you again for the kind introduction. I'm Sanaz. I'm a process development engineer in Beneq, and today I'm so happy to be here, and I'm so excited to talk about our recent developments at the intersection of material science and quantum physics, which is thermal atomic layer deposition for superconducting tinitride thin films using our Beneq TFS 200 reactor. Here is a quick roadmap for our 2 days presentation, including the motivation and background, thermal ALD growth of tinitride films, the characterization techniques that we use, both the structural and also the kind of the superconductivity behavior characterization. And then I would briefly talk about our future development plans about kind of tinitride and also other superconductive thin films. Now, let's talk about the importance of superconductivity. Why do we care about it? Let's talk about their role in high-performance computing and quantum technology. Superconductors are a fundamental component in quantum computers, where they allow for the creation of qubits, which are the building blocks of quantum computation. Unlike classical computers, which use binary bits like zeros and ones, qubits can exist in multiple states simultaneously, enabling computations that are impossible for even the fastest supercomputers. Beyond computing, superconductors are critical in scientific instruments like MRI machines, particle accelerators, and fusion reactors. They allow us to generate extremely strong magnetic fields, which are essential for high-resolution medical imaging and fundamental physics research. And finally, superconductivity plays a major role in microelectronics. As computing demands increase, we need materials that can operate faster with minimal energy consumption. Superconducting interconnects, detectors, and memory elements are pushing the boundaries of what's possible in modern electronics. However, to harness these benefits, we need superconductive materials that are reliable, scalable, and compatible with modern microelectronics, which bring us to thin film superconductors. Superconducting thin films are essential for integrating superconductivity behavior into real-world applications, particularly in microelectronics. For instance, superconducting interconnects in ICs, the integrated circuits, can drastically reduce energy dissipation and signal delay. Superconducting memory elements, such as superconducting RAMs, promise ultra-fast, non-volatile storage. And superconducting tunnel junctions in sensors and detectors enhance sensitivity and performance. But developing superconducting thin films is challenging because the thickness and the uniformity of the film greatly influence superconducting properties. Impurities and structural defects can disrupt electron pairing, which reduces superconducting performance. Interface quality is also critical. Poor adhesion or composition variation can degrade superconductivity behavior. To overcome these challenges, we need a precise fabrication method. This is where ALD shines. ALD enables atomic level thickness control, uniformity and conformality, along with high quality thin film deposition, which is scalable and reproducible. Now, let's focus on one specific material, titanium nitride or tinitride. It has a high chemical and thermal stability, making it robust for various applications. Tinitride thin films have been used in quantum bits, the qubits, kinetic inductance detectors, and superconducting tunnel junctions, showing reduced dielectric losses compared to traditional superconductors like niobium and aluminum. Also, tinitride exhibits a superconductor insulator transition at the limit of disordered films, making it an interesting material for fundamental superconductivity studies. But the position of high-quality tinitride thin films is not easy. Let's look at the ALD process and its challenges. Here in Beneq, our plan was to develop a cost-efficient superconductive tinitride in the beginning. That's why we chose thermal process using TiCl and ammonia, or titanium chloride. In the atomic layer deposition of tinitride with these precursors, the process follows a series of well-defined reactions at the molecular level. First, which you can see in here, when the TiCl absorbs onto the surface, the metal center of that precursor undergoes reduction, leading to the partial loss of the ligands. Next, ammonia, that you can see in here, plays a critical role in completing the process by removing the remaining chlorine or amine surface species, forming the desired tinitride layer. One important parameter, so this is the first half cycle, which we pulse TiCl into the reaction chamber. This is where we purge TiCl from the reaction chamber, and this is where we introduce ammonia to our reaction chamber in order to complete the formation of tinitride thin film. And then we repeat this cycle for as many times as we want in order to get our desired thickness. One important parameter in this reaction is to use high enough deposition temperature, which is at least 325 degrees centigrade, as TiCl has strong titanium and chlorine bands. The ligand byproduct is cross-corrosive, and it needs good desorption to avoid chlorine residues. Plus, slow kinetics, as you can see here, that slow kinetics at lower temperature prevents self-limiting growth. Growing high-quality tinitride thin films using ALD is not as straightforward as it seems. Here you can see the main challenges in growing a uniform tinitride with ALD. These challenges can affect film uniformity, conductivity, and overall performance. Let's go through these challenges one by one. The first one is the nucleation and growth issues, which is one of the first obstacles, and its nucleation delay, especially on non-reactive surfaces like silicon dioxide and alumina. Since these surfaces do not readily react with the tinitride precursors, the film takes longer to start forming, and this delay can cause island growth, also known as the Volmer-Weber mode, where small metal clusters form before merging into a continuous film. The problem? This leads to non-uniform film thickness and roughness. Moreover, unlike oxide ALD, where growth is often smooth and layer by layer, these metallic films like tinitride tend to grow in a three-dimensional island mode. That's kind of that mode that we just mentioned. This happens because of high surface diffusion, making it harder to achieve uniform thickness across the substrate. The next main challenge is the precursor chemistry limitation. For a successful deposition, the precursor must fully react with the surface. But in reality, we often see incomplete surface reactions, causing the thickness variation. Certain precursors like TiCl can also leave behind unwanted ligands, coloring contamination, which is a common issue. And also, if you're using organic precursors like TD-MAT, it also can have a carbon contamination. The third main challenge is the film density, film quality, which is film density and conductivity issues, meaning that not every tinitride film is superconducting. Even if we overcome nucleation and chemistry challenges in order to get a uniform film, the film density and conductivity are still critical factors. During early growth stages, the film can have higher defect densities and grain boundaries, which cause porosity inside of the film structure. This impacts not only the mechanical stability of the thin film, but also the electrical properties, which is essential for superconductivity. For superconducting applications, precise control of the titanium and nitrogen ratio is crucial. Small deviation can shift the critical temperature, which is a really important or almost the most important parameter in superconducting materials, and increase resistivity, which affect the performance negatively. But I'm pleased to share that in Beneq, we successfully deposited a uniform, high-quality tinitride thin film using thermal ALD in our TFS200 reactor, which operates at 450. These films were then carefully optimized to exhibit superconductive behavior under tightly controlled processing conditions. The key deposition parameters, such as cycle length, growth per cycle, and overall growth rate, are summarized in this slide, as you can see here. And this is also a picture of our TFS200. This reactor, which is shown in here, is not only an excellent platform for research and development, but also highly suitable for small-scale production, bridging the gap between academic and innovations and industrial applications. Now, let's go to the characterization part. In order to evaluate the uniformity and thickness of our tinitride films, we perform spectroscopic ellipsometry characterization. However, conducting ellipsometry on metallic films like tinitride presents unique challenges. Unlike dielectric films, metals have a complex optical response, making them difficult to model their refractive index and extinction coefficient accurately. Additionally, surface roughness and grain boundaries can introduce measurement inconsistencies. That's why, first, we perform reflectance measurement using Agilent spectrophotometer. This step was crucial not only for improving the mathematical fit of our model, but also for ensuring that the model accurately reflects the true physical properties of tinitride, rather than just an optimized numerical approximation. We carefully designed our measurement using three different angles of incidence, allowing us to achieve a more precise fit that aligns with the fundamental physics of tinitride. Here, you can see the results for the refractive index and extinction coefficient across different wavelengths. This is the wavelength range, providing valuable insights into the optical behavior of our tinitride that we use to optimize our ellipsometer model. Despite these challenges, we successfully performed high-precision ellipsometry measurements thanks to our senior scientist, Dr. John Ron, ensuring the accuracy of our results. A key indicator of measurement reliability is the mean squared error, as you can see here, MSE value, which quantifies the fit quality between our model and the experimental data. Our measurements exhibited exceptionally low MSE values, confirming the precision of our thickness and optical property analysis. At Beneq, we place great emphasis on MSE values, carefully refining our models to achieve the most accurate and reproducible results possible. After getting to know the the thickness of our film, and uniformity, we perform 4-probe conductivity measurement at room temperature using Oscilla 4-probe tool to evaluate the electrical properties of our tin nitride. It's important to note that the typical resistivity of tin nitride at room temperature ranges between 100 to 400 microohm centimeter. One particularly interesting finding from our measurements was that by increasing the ammonia purge duration, the resistivity decreases, which may be due to the lower coloring contamination and better crystallinity of the film. And then let me go to the next slide. And then for further structural characterization, we perform focused ion beam scanning electron microscopy. It was our initial attempt to use that method, but due to the resolution limitations for our thin film, we were unable to obtain reliable cross-sectional images directly. Instead, we used this method for lamella preparation to enable high-resolution TM analysis. The process involved precisely milling a thin section of the sample while ensuring minimal damage. To enhance the mechanical strength and prevent structural deformation, we deposited a protective platinum layer on top of the film before thinning it down to electron transparency. This careful preparation allowed us to obtain high-quality TM images, ensuring that the film's microstructure and grain boundaries could be accurately analyzed. Now, let's take a closer look at the TM cross-sectional analysis of our tin nitride thin film. The image clearly reveals the layered structure of the sample consisting of the silicon wafer, the substrate which you can see here, silicon dioxide, which is this layer, as you can see, the dielectric layer on top of the silicon wafer, and then the deposited film of tin nitride. And in these images, you can also see the platinum, which was the protective layer from lamella preparation. One of the key observations in this TM image is the polycrystallinity of our tin nitride film. The presence of multiple grains, as you can see in here, these are multiple grains with different orders, with different orientations and orders, confirms that the film is not single crystalline, which is expected for tin nitride films deposited by ALD. However, despite this nature, the homogeneity of the film thickness across the silicon wafer is excellent, demonstrating the uniform deposition achieved through ALD. Polycrystallinity can have an impact on superconducting properties, like kind of negatively affected, as grain boundaries may act as scattering centers for electrons, potentially affecting resistivity and superconducting transition temperature. Understanding these microstructural characteristics is essential for optimizing the film's performance in superconducting applications. Overall, the TM analysis confirms that we successfully achieved uniform tin nitride deposition across the wafer with well-defined interfaces between the layers, validating the precision and repeatability of our ALD process. Then, for the chemical composition analysis, we perform TEM EDX mapping on a random spot of our tin nitride film, as well as across the entire cross-section horizontally to examine the elemental distribution within the layers. As expected, the presence of titanium and nitrogen is clearly visible here, nitrogen and titanium. And also, you can also see the peaks over here. However, you may also notice that titanium and nitrogen signals overlaps. This is due to the close energy levels in the EDX spectrum, which makes it challenging to fully separate their contributions. In addition, we detected coloring contamination in the tin nitride film. This is a direct result of using a chlorine-based precursor. and chlorine incorporation can sometimes affect the film's properties, particularly its electrical conductivity and superconducting behavior. To quantify the impurity content in our tin film, in our tin nitride films, we perform time-of-flight elastic recoil detection analysis known as tough air dog. This technique also allowed us to evaluate the stoichiometry of the films, which showed a nitrogen-rich tin nitride composition. This slight excess of nitrogen plays a beneficial role in several ways. It helps suppress titanium vacancies, which otherwise act as scattering centers and degrade superconductivity. It also prevents the formation of non-metallic titanium phase, such as titanium to nitrogen, which are less conductive and do not exhibit superconductivity. Instead, it stabilizes a more stoichiometry and metallic tin nitride phase, which is essential for achieving robust superconductive behavior. In addition, a slightly nitrogen-rich composition supports the formation of a cleaner rock salt tin nitride crystal structure, lowers the incorporation of impurities like oxygen and chlorine, and improves long-range crystallographic order, which is critical for coherent electron pairing or Cooper pair formation at the heart of the superconductivity performance. It's important to keep the chlorine content below 1 atomic percent, as chlorine is corrosive and can degrade metal-based films over time. In thermal ALD, increasing the deposition temperature helps reduce chlorine incorporation, and in our case, chlorine levels remain below 1%, which is within the acceptable range. Oxygen impurities, on the other hand, can significantly impact the superconducting properties of our tin nitride. Oxygen tends to form titanium oxynitride transition layers on the surface, which can alter both the electronic structure and the superconductive behavior. Therefore, to maximize superconducting performance, it's essential to minimize oxygen incorporation during deposition and post-process. Now, despite the presence of some chlorine contamination, we have great news. Our tin nitride film still exhibits superconductivity behavior. To verify this, we use the physical property measurement system called PPMS to measure the critical temperature using the field-cooled method with the vibrating sample magnetometer. For those less familiar with VSM, the vibrating sample magnetometer, here's a quick explanation. The sample is placed in an oscillating magnetic field, and as it vibrates, the induced magnetic momentum is detected. This setup allows us to precisely monitor how the magnetic properties change as the temperature decreases. And here's where it gets really exciting. We observe the Meissner effect, which is the hallmark of the superconductivity in here. The Meissner effect occurs when a material expels an external magnetic field below its critical temperature, confirming the transition into the superconducting state. In our case, we observed the onset of the Meissner effect at 3.8 Kelvin, which is right here, and it is stabilized at 2.5 Kelvin for a 60 nanometer, 2.5 Kelvin in here, for a 60 nanometer tin nitride film. This is a strong indication that our grown tin nitride has successfully entered the superconducting state, even in the presence of chlorine impurities. To put this text in context, previous studies using the same precursors and thermal ALD reported much lower critical temperature values, like 1.6 Kelvin for a thicker film of 150 nanometer and also 1.35 Kelvin for a 75 nanometer film. It's worth noting that the film thickness tends to lower critical temperature due to quantum confinement and surface defects. For comparison, bulk tin nitride has a critical temperature of around 6 Kelvin. So achieving 3.8 Kelvin on set and 2.5 Kelvin stabilization in a 60 nanometer film is an impressive result, showing that our deposition process not only yields uniform films, but also preserves superconducting properties remarkably well. To wrap things up, we have successfully developed a cost-efficient superconductive tin nitride thin film with high uniformity using thermal ALD with our Beneq TFS200. Here's a quick summary of our key findings. The deposition temperature was 450 degrees and the growth rate was 2.43 angstrom per minute. The final film thickness was 60 nanometers and the optical properties was like the refractive index was 0.92 and the coefficient, the extinction coefficient value was 2.32 at 633 nanometer wavelength. The room temperature resistivity was 114 microohm centimeter and the superconducting transition temperature range was from 3.8 to 2.5 for a Kelvin for a 60 nanometer film. Interestingly, our thermal ALD approach has yielded highly promising results with both superconductivity and room temperature resistivity values that compare favorably to reports on plasma-enhanced ALD tin nitride from other studies from industry. This highlights the strength of our process in achieving high-quality films without the additional complexity of plasma-based methods. Now, where do we go from here? Our next steps include developing plasma-enhanced ALD tin nitride to explore how plasma-assisted deposition impacts superconductive properties, and then in the investigation of niobium tin nitride as a promising alternative with potential improvements in critical temperature and performance. Further characterization of the current films to refine deposition conditions and push the boundaries of thin film superconductors are also in the list. Before we move on to the question and answer session, I would like to take a moment to express my sincere gratitude to everyone who contributed to this work. First, a special thanks to Dr. John Wren, our senior scientist, whose deep expertise in optics quite literally saved us on countless occasions, especially during the challenging process of alexometry model development. I would also like to thank Dr. Dilek Chakroglu for her kind support with the room temperature conductivity measurement. My appreciation also goes to our collaborators at Aalto University who are doing outstanding work in low temperature physics. Their insights and contributions have been instrumental in moving our research forward. Thanks also to our partners at the University of Uvascula for performing the tough layer dub measurements, which provided key data on impurity quantification. And thank you all.
Thank you, Sanaz, for sharing your valuable insights with us today. So,
yes.
Participants, you have any doubts regarding whatever has been discussed? So you can ask questions.
Yeah, hi. So you Hi, Dr. Zarabi. Thank you. So you just discussed about that verification by Misner effect by performing that measuring the transient temperature. I think this critical temperature.
Yes.
So can you hear me?
Yes, I can hear you. Yes, we did that one. So
Yeah.
we actually, yes, go on.
So just you highlighted that there was a reason for that higher TC, that quantum confinement was there.
So the reason, so actually, if we want to be honest, 3.8 is not a really high super critical temperature.
That was comparative one. So the comparative what you have shown there in the literature. Yes.
Yeah, exactly. So, but when it comes to thin films, especially the kind of the nitride thin films, it's a great value. So we always need to keep this in mind, that all those values that we are talking about, they are relative. So because, the bulk tin nitride is 6, but, we have so many other superconductive materials which have at least kind of 20 Kelvin as their critical temperature. So that's why it's important to keep that in mind, that what context we are talking about. And the reason that we achieve that great performance, I can say that it's like that our reactor provide a really great kind of vacuum and also a good environment. So we minimize the oxygen contamination. So that's one reason. And also the process that we had, the process was like kind of fully optimized. So we reduce the level of other contaminations like coloring, because for instance, if you do not optimize the pulse and purge times of your ALD process, then it will cause more contamination levels, and those contamination levels can affect your TC.
Okay. So what I mean to understand is that you mentioned that quantum confinement is one of the reasons for there. I think I'm correct.
Yes.
I heard you correct. Okay. So is there any conclusive evidence regarding that, or you have just followed the literature, or there is some particular link with the experimental data you have shown?
So, well, actually, those kind of interpretation was done with our Aalto University collaborators, which are our quantum physics experts. So,
Yeah.
but yeah, I can actually, we have the literature for that. If you want me, so you can just email me, and then I will send you.
Okay. So yeah, that is fine. That's fine. Thank you.
Of course.
So thank you for.
Okay, thank you, Sanaz, for sharing your insights.
Of course, my pleasure.
Anybody has any doubts?
Hi, Sanaz. Shubhra here.
So
So
anyone
your
has any
presentation was
doubts, they can
brilliant.
mail on
Yeah, sorry.
laserscience@co.in.
Can you hear me, Sanaz?
Yes, go on.
Yeah. Okay. So I'll just ask a quick doubt. So one of my customers, they were at first interested in pursuing a ALD setup, but then what happened is they are not feeling confident in handling the precursor gases, because as you can see, yeah, like you are experienced, lots of chemistries are involved, and this person is from physics department again. So my doubt is whether now Beneq can also help
I
in
think I missed the
giving some
correct
training.
email address. It's ls_marketing@laser laserscience.co.in.
I think they are not able to hear us.
Hmm.
Just one question.
So, well,
Um,
about regarding your question, we actually have a support system. So we have a support
oh,
system for our customers even after kind of selling the tool. So our
okay.
customers are getting in touch with us through email, through different meetings, and even when it's necessary, we're gonna go on site to help them.
Okay. So it's like even in handling the very reactive gases, some basic training can be given from Beneq
Yeah,
side, right?
exactly. I also have training courses for in different levels. It can be the process optimization to the kind of the tool assembly, the kind of the source handling, things like this.
Okay, great. Because I have to then again go back to him and then mention that now Beneq has the capability of also giving you such type of training, so they can also again look back in procuring an ALD setup.
Yeah,
Yeah.
hopefully.
Yes. Thank you, Zanab.
Pleasure.